In the previous lecture, we were able to see how the one pulse experiment, we did a 90-degree Y, we started with the equilibrium density matrix and we did acquisition. We were able to see how the expectation value came up to be having e power I omega t, which one Fourier transform is going to give you a single resonance at plus omega. In this lecture, an introduction to on how the density matrix can be visualized as a vector in the three-dimensional space of Ix, Iy and Iz. So for instance, if this is your density matrix, basically the projections of it could be given as a set of coordinates in Ix, Iy, Iz. So therefore, a density matrix at any given point could be given by the value of its projection times the vector itself. And this would once again help you understand how when you apply a few things. For instance, if you want to determine what is sigma of t and you have a certain propagator minus I omega t I of I, and you have an initial state which is ij, we'll be trying to deduce what will be the final value based on these type of operations. So basically you are able to understand your Hamiltonian times t could be given by omega t times ii, and that's what is written here, and this could be your initial density matrix. Of course, in this case, we are trying to imagine the omega is time independent. Why don't we try to expand it, where the sigma 0 is ij minus it by 1 factorial times ii comma ij. But remember that the omega is also part of the Hamiltonian, so omega will be here. I'm not committing to what is omega and what is t. If you're trying to get a flip angle done, then omega tau p will be equal to alpha. On the other hand, the omega tau p could also be capital omega I times t, which could be a chemical shift type evolution, which we saw in the previous lecture. So let me write the solution in the form of BCH formula expansion. So the advantage that we have here is that these are cyclic commutators. So I'm going to take the omega up here. I'm going to take the omega square into this. So this is going to be ij minus I omega t by 1 factorial. And you have a ii comma ij. This is going to be equal to epsilon ijk, where if it's cyclic, it's going to be plus 1. Acyclic is going to be minus 1. You're going to get ik. We have taken the square of omega outside, so I omega t the whole square by 2 factorial times ii comma epsilon ijk times, I missed an I here, iik. The first one was cyclic. The second one would become acyclic, meaning that, let's say, in this case ijk was plus 1, you're going to have ik, which will not be cyclic anymore. So therefore, this term would end up cancelling this to get a minus 1 here times I. So therefore, you're going to end up getting minus I square times ij. And minus I square is nothing but plus 1. So basically, this entire term becomes ij minus I omega t the whole cube by 3 factorial times ii comma ij. And you are once again able to appreciate the fact this ends up going wherever you started. So therefore, this can be simplified as epsilon ijk times I times ik, and so on. So now this can be simplified as ij taken common out. You're going to have 1 here that comes up to this term, and you have plus I square, which will be minus 1. So you're going to end up getting minus omega t the whole square by 2 factorial and this is going to be ij, so that's going to be as it is, plus omega t power 4 by 4 factorial if you take the next term, and so on. So similarly, the next one that will end up coming here, remember you have an I times I, that will be minus 1, so the minus will become plus. So therefore you are going to end up getting plus epsilon ijk ik multiplied by omega t by 1 factorial. I power 4 will end up coming, which will be plus 1, therefore the minus would remain, so minus omega t the whole power 3 by 3 factorial, ik would come back, which we have taken out, plus omega t power 5 by 5 factorial minus, and so on. So this gets therefore reduced to ij times cos of omega t plus epsilon ijk times ik sine of omega t. So let me rewrite what we started with. We started with ij upon operating with a Hamiltonian, which is given by omega times, this omega could be anything, times I for a duration of t. Basically this results in exp minus Hamiltonian t times ij exp plus I Hamiltonian t. Of course, in this case we are assuming the Hamiltonian is time independent, which it is. You get the solution as ij cos omega t plus epsilon ijk ik sine omega t. So let's take a few examples to understand this better. I'm going to draw a table here. So let's start with ij, and then we can have an I here, and then we can write the answer. So let's start with the fact, let's say ij is iz and ii is also iz. You would realize the commutator would end up giving you iz back. When ij is equal to I, you would end up getting no change. On the other hand, let's say ij is ix, you can keep ii as iz. If you operate it here, ij will come back because you started with ij cos of omega t. Then you have an epsilon ijk, where how did you have this epsilon ijk come up? It ended up coming for a commutator between ii and ij, where you had ii comma ij giving you epsilon ijk ik. If ii is z, ij is x, it is cyclic, so therefore you get a plus 1 plus iy sine omega t. Finally, let's say your ij is iy and you still have ii as iz, then you start with iy cos of omega t, then you have ii as iz, ij as iy, you see that it's acyclic, so you have minus ix sine omega t. This is quite straightforward to imagine. Let's say this is the x and y axis and the z axis is what you're looking directly onto. Then what we are able to understand here, when you started with ix, the ix comes up nothing but the cos part of it, cos of omega t plus iy sine omega t. So you're talking about counterclockwise rotation. So similarly, when you're going with iy, let us say this is what you're having, you are able to immediately understand this would end up resulting in a projection that has a minus ix. So one could immediately understand all these are exactly the similar type of rotations that we had seen before, where you had an effective field. Now the effective field is given by the ii operator and your initial density matrix is given as the ij. Therefore, you can easily determine what will be the solution based on the rotations that end up happening. Once again, this makes it very clear why rotating iz along iz gives you iz, because there will be no change that ends up coming. So now let's expand this table so as to make it even bigger. We had just seen examples where we had kept ii as z component and we have arrayed j across x, y and z. Now let's take different components for ii. Let's take ii as ix, and ij as ix, iy, and iz. The first answer is very simple. There will be no rotation that comes up if you're rotating along ix when you started with ix. On the other hand, when you're rotating along x, when you start with y, you're going to have cos of omega t. And then now you're talking about a rotation that is counterclockwise along z. So therefore, what you're going to have I, comma, ij is going to be epsilon ijk is going to be plus 1. So plus iz of sine omega t. So similarly, when you start with iz, you're going to get iz cos omega t. Now x comma z will be a minus 1 minus sine omega t. So now let's say for an instance omega t is equal to alpha, you are able to understand if you started with the equilibrium magnetization, you applied a y phase pulse, you're going to end up with a minus iy. This does make sense. When you had equilibrium bulk magnetization along z, applied a pi by 2 pulse along x, then you had the minus m naught along the y-axis. This we had seen in the classical case. So let's keep continuing where we have iy, ix, iy, iz. Iy on iy is going to be iy. Now this is going to be ix of cos omega t. It's very easy to start the first one, put the first one here and put the cos part there. Now comes the question of iy comma ix. Since this is acyclic, you're going to have minus iz sine omega t. On the other hand, here it's going to be iz cos omega t plus ix sine omega t. All these are right-handed coordinate system with a counterclockwise rotation that gives you the final answer. So once again, let us say you had set alpha as pi by 2 when you started from equilibrium, and let's say you apply a pi by 2 y phase pulse. Here it will go to alpha, cos of 90 will be 0. So you have the magnetization along the x-axis. This is what you saw in the bulk case. Here what you are able to see is that the density matrix end up coming along a given phase. The moment you know how the density matrix is going to look, all that you got to take is take the product between the density matrix and the observed I plus or I minus operator, find the trace and figure out what will be your solution.